Hello, everyone. I will start with a slide deck. Okay. So today we'll be talking about image processing in driverless AI. And for the agenda, we'll have a couple of points. So firstly, we'll discuss what are the available approaches to use images inside driverless AI. Then we will talk about how we could prepare the data to pass it to the driverless. Then we will cover in detail the two approaches we have, image transformer and image auto model. And then we'll have a demo showing the capabilities of what we have inside. Yeah, and at any time, just like feel free to ask questions, and I'll be happy to answer. Okay, so let's start with what we have in driverless. So basically for the image modeling, we have two major approaches. The first one in the left is called embeddings transformer. And it is the approach that we are using by default. So whenever you're creating the experiment with image data inside, then we will be using this embeddings transformer by default. So what it is doing, it converts the input images to the fixed embedding representation. And afterwards, as a result of this transformer, our images are transformed to their vector of numbers. And then this vector is used for the modeling inside driverless. And it follows the usual driverless workflow. So this vector is passed through the usual like LightGBA, MixGBoost, GLM models in driverless. And it allows us to work with the mixed data types. So it means that if you have a data set with images, text, tabular data, and you want to model everything simultaneously, then you could use this approach. And as a result, driverless will concatenate all the features together. So we'll concatenate these embeddings from the images to the other features. And we'll use it as a final data set to model, to create models. And another advantage of this approach is that it could run even on CPU. So it means that if you don't have a lot of computational power and you don't have GPU machines, then it is fine to run it even on CPU, as it is quite fast and it does not require any large resources to be run. Another opportunity here is that it allows fine-tuning. It means that initially, by default, we are using ImageNet pre-trained models. So we are using all the models that were pre-trained on the ImageNet dataset. And afterwards, you have an opportunity to allow fine-tuning on your particular dataset. So what it means is that instead of using fixed embeddings, vector representations from the ImageNet, we will fine-tune the model for a couple of epochs on your particular dataset. And it allows us to obtain kind of like embedding space that is closer to your dataset. And most probably it will produce better results than pure ImageNet weights. And finally, this approach also supports modular C++ scoring pipeline. So it means that if you want to download the scoring pipeline for the deployment of this model, then you could use C++ module. And the second approach, it is here on the right, it is called automatic image model. And this approach is kind of like true AutoML for the images data. So in this case, instead of using just fixed embeddings representation from the images, we will actually train the neural networks end to end. But the limitation here is that it works only with a single image column. So it means that if you have like mixed data set with different features, with tabular and text features, then it is better to use this first approach. However, if you have only the images in the data set or the images kind of the main driving power of your data set, then it is better to use automatic image model. Another peculiarity here is that you should use it on the GPU machines. So it still runs on CPU, but it will be quite slow even for small data sets because we're kind of like training the models end to end, and it requires much more resources compared to the embeddings transformer. And the main advantage here is that it basically does all the automatic hyperparameter and model selection. So you do not need to worry about anything in the neural networks, about architectures, and so on, and everything is done automatically. And for now, it supports the classification and regression problem types. And speaking about the different problem types, so basically, the first and the most frequent model type for the images is, of course, classification and regression. And we have already it in driverless. And now we are working on other problem types to add these capabilities. So the next step will be the semantic segmentation. So in this case, instead of just classifying the whole image, we need to classify each pixel, each individual pixel in the image. And we need to say in this case, where is the cat located, where is the grass, and so on. And afterwards, we'll be moving to object detection and instance segmentation. So in this case, instead of having just a single class for all the dogs, you need to separate the instances of each individual dog and each individual cat in the image. And also you need to either draw a bounding box or draw a mask for the instance segmentation. And so we already have some working prototypes, and we are working on implementing it into the product. All right, now let's move on how we'd like to, how we can upload the data set to the driverless. So basically we have lots of different opportunities for uploading images to driverless AI. The first approach, and probably the easiest one, is that you just need to create a single archive file with the images inside. And afterwards, you could upload this, for example, zip archive directly to the driverless. And driverless will infer that there are images inside, and it will create a data set that contains these images. Also, apart from pure images, you could also provide a CSV file if you have some additional features for the images. And in this case, again, driverless will use this CSV file, and it will concatenate them with their images that you have provided in the zip archive, for example. Another opportunity is if you have really large data sets with millions of images, then of course it is infeasible to download, upload the whole data set to driverless. In this case, you could just provide a CSV file with a physical path to the images on the disk. So it means that now instead of uploading the images directly to the driverless, all we need to do is just create an additional column in the CSV file where you're specifying their absolute number, absolute path to their images on the disk. And again, driverless will infer it and use it for the modeling. And finally, the final way to upload the data is again a CSV file. But in this case, instead of using their local paths, you could actually use remote URLs. So if you have your images stored somewhere in the cloud, or if it is stored somewhere just on the internet, then you could just provide the URLs, and again, driverless will infer and use them for the modeling. And also, apart from the images, like this approach allows us to work also with their video and audio data. So basically, what you need to do is you need to prepare your data beforehand before uploading it to the driverless. And we have a repository. So here's a link is at the bottom of the slide. It is a public repository with the recipes that you could use to kind of enhance driverless capabilities, default capabilities, with some additional features if you'd like. And we have examples there for their video and audio manipulations. So what we need to do in this case is, firstly, we need to, for example, in this case of video, we need to process the video and save the individual frames. So in this case, for example, we need only the faces of the person. So we're just saving the faces to the disk. And afterwards, we could upload the images directly to the driverless and use usual image approaches. And also, we could make the similar stuff with audio. So kind of like recently, like the most frequent way to handle audios is, again, we are firstly transforming them to the images. And these images represent their like MEL spectrograms of the audio. And afterwards, you could upload these images to work in driverless. So it means that we could also work with video and audio classification. Okay. All right. So now let's speak about these two approaches a little bit in more detail. So the first one is image transformer. And in this case, as I have already said, we are using their image models and the weights that were pertained on the ImageNet. So ImageNet is pretty huge data set with millions of images and thousands of classes. And it allows us, instead of like training the models from scratch, to start from pretty good point. And in this case, we could just use their our convolutional neural networks as either as a fixed feature extractor. So it means that we are not changing any weights and we are just using the ImageNet weights. Or as I have already said, we could fine tune it for a couple of epochs and only then use this embedding representation. And so what this actually embeddings mean? So for example, here we have some architecture. I guess it is ResNet 34 architecture. We have some input image and we have some hidden layers in the model. So the image is gone through all these layers. And here in the end, we have this average pooling. So it is the pre-last layer of the model. And we could use this pre-last layer as our vector representation of our images. And afterwards, we are passing all our input images through the input networks. And we take just this pre-last layer that allows us to get this vector representation. And we put these vectors into usual models, right? Into the classic machine learning models. And we use them as just additional features to in our models. So it is this first approach, the image transformer. The second one is image auto model. And again, as I have already said, it allows us to automatically select all the hyperparameters, and it chooses everything for us. So starting from their like different hyperparameters for the neural network. So we're selecting the learning rate automatically. We're selecting the optimizer. Also, we're selecting the optimal batch size and input size of the images. So if we have super large images, then most probably we will suppress them a bit. Or if we have small images, then we will, on the contrary, make them larger. Also, we're selecting here the architecture, so the best architecture that works for your particular data set. And also, apart from these parameters, we're also like make the whole training process also automated. So it means that we are selecting the number of epochs the model is training for. We're selecting the cropping strategies of the images, the augmentations we are applying during the training, and also the learning rate schedulers. And speaking about the architectures, like we are using also well-known recent architectures, including like such families as SERISNets, efficient nets, dense nets, and so on. We are not developing any new architectures. So it means that we always start with a known architecture and we are fine-tuning it on your provided data set. It means that we are not changing the architecture itself. However, like for different problem types and for different data sets, like various architectures work in a very different way. And that is why we need to optimize what is the best architecture for a particular provided data set. Speaking about the image preprocessing, as I said, we're like make automatic selection for the cropping strategy. It means that sometimes if we have some input image, we could either just crop some random region from this image, or we could resize it. And the reason for this is because we need to pass to the model the images of the same size. And in the data set, you could have images of different sizes. And that is why we need some mechanism to kind of transform all your images to the same size. And in this case, we have like these approaches, like either this resize or crop, or we could even combine them together. First applying resize and then cropping, randomly cropping from the image. And once we have like created a data set with the same size images, we could apply the augmentations to the data set. So it means that like we want to cover all the possibilities that could present in our data set, and maybe we have a small data set and we want to make it more diverse. And in this case, we could apply different transformations to the images that do not change the classification label. So here you could see a couple of different augmentations examples and how their output image looks like. And also, apart from also like well-known augmentations, we are using the mix-up augmentations. And this idea is presented here on the right. So the idea here is if you have like two images, for example, cat and dog, then we could mix them together and obtain some kind of like middle representation of the cat and dog. And in this case, we will use like the labels 50% for the dog and 50% for the cat. And again, it allows our model to generalize better for the new images in the test data set. And here on the slide, you could see our current results of this automatic image model approach. So we're evaluating the results on the past Kaggle competitions. In this manner, it kind of allows us to estimate how well our models are performing against like real persons, real data scientists in the past Kaggle competitions. And here, this red bar represents as a percentage, the top percentage of the leaderboard that model achieves out of the box. And as you can see here, it almost always performs in the top 20% of the leaderboard, and sometimes it performs even better, like in top 5 or top 1%. So it works pretty good. And again, it doesn't have any like prior knowledge about the domain. So it means that here you could provide any images from any domain. So either it is just like classification of cats and dogs, or it is some medical images, or like chest X-rays or CT scans and so on. All right, so it is the end of the slides, and probably I will stop here for a bit, and maybe do you have any questions so far on these slides?
I don't see any questions coming in, Yauhen. But if anyone has a question, please send it in the Q&A tab or the chat tab.
Okay, so yeah, so I will go to the demo, and in the meantime, you could send all your questions, there. So all right, so let's move to the driverless, and let's see how we could use the image data inside driverless. So firstly, we need to upload the datasets to the driverless. So here I have already uploaded a couple of datasets, but I will just show you how it is done with different approaches. So the first approach is like increase it a bit. Okay, so the first approach is like if you have a directory with their images, and here you could see that we don't have any like CSV files with the labels or anything else. So it is just directory with the images. And here are some images of the cars. And what we could do is just to zip these images into a single archive file. And afterwards, we could just upload it to driverless. For example, here, just directly drag and drop. And here you could see the driverless creates a new data set with this name, carexamples.zip. And if you go to the details, it shows us just here a single column called image. So it inferred that it is image type. And it created a single column because we don't have any other data. And also here in the datasets rows, if you click on this button, you could see the preview of the images. So here we could see that all these like images that we have uploaded are here. And also you could see the relative path to the images on the disk. So what actually driverless has done is we have uploaded this dataset there, and now it unzipped it, and it stores the images on the disk, and we have this relative path to the like to the actual image on the disk. Another opportunity is you could provide the directory structure inside your directory with the images. So for example, if you have two classes, class 1 and class 2, and each of them contains multiple images, then you could also like just zip all the directories together into a single archive and upload it to driverless. So in this case, it is this archive. And driverless will infer this directory structure, and it will infer that we have two classes in this dataset. And it will create, in this case, now two columns. The first one is image, and the second one is label. And here we could see that we have these classes 1, 1, and 2 from our dataset. And finally, the final opportunity is you could also add a CSV file to their to a directory with the images. So in this case, I've just created a like simple file with additional features. So in this case, we need to provide their image name, and also, for example, these two random features, feature 1 and feature 2. And again, if you now combine everything together and upload it to the driverless, then it will look in the following way. So now we will have these three columns. So the first one is car ID with the image, and then these two additional features that were presented in the CSV file. And again, if you click on the preview, then we could see these images and additional features as well. So now, having uploaded the dataset to driverless, we could use it for the modeling. And I will proceed with their car example. So here I have a dataset with 35,000 images, together with some additional features. So I will click on dataset rows, and here you could see that we have like images of the cars together with some additional tabular data like manufacturer, model year, category, and so on. And also we have here in this case the target variable was price. So we need to predict the price of the car based on its image and other parameters. So to model this dataset, all we need to do is use the usual driverless workflow. So we click predict here, and we're creating a new experiment. So we could select the target column, in this case price. And afterwards, we could just go straight and click launch experiment. So we do not need to change anything in the settings or change like anything in the dataset. So driverless will automatically infer that it is images, and it will apply a corresponding image transformer to the images. So as we have discussed in the slides, the default approach in driverless is this image transformer. And here in the experiment preview, you could see the list of pre-trained image architectures. So it means that it is the architectures that we are using for the modeling. And by default, we are using the exception architecture. So it is the one that is selected by default. So we could now just click launch experiment, and it will start modeling the images and tabular data together. And it could take some time. So I have pre-run a couple of experiments. So for example, this experiment with car prices, it has already finished. And here in the variable importance, you could see a list of top features. And on the top, we see some tabular features like the engine volume, the gearbox, the year of the car. And together with these features, we have a mix of image features. So in this case, they are called image vectorizer. So it is the vectorizer that transforms our images to the embeddings. And also we could see the name of the architecture. So in this case, it was ResNet 34. And it was also a mix with EfficientNet B0. So in this case, we have the mix of different architectures. And the last number is just represents the component of our feature. So for example, if we have 25 components in our embeddings, then this seventh component was from this ResNet 34 architecture. And the final model here, so here we have our features. And the model here is light GBM. So it means that we just concatenate all these features together and pass them into the light GBM model and let driverless decide what are the best hyperparameters, what are the best features to use in these light GBM models, and so on. So it is just the default approach that you could use just clicking launch the experiment. However, you could also tune the parameters a bit, and we have all the control over what you could change in their image transformer. So for this purpose, you need to go to the expert settings. And in the expert settings, we have an image tab. And here we have a list of settings that you could change for the image transformer. So the first one is the list of architectures that you want to use for the modeling. So here, as I said, by default, we are using only exception architecture. However, you could select multiple ones from here. And basically, we don't have here like lots of models. We have only a list of 10 architectures. And the idea here is that they represent just different families of architectures that could be used for the modeling. And also, you could select multiple ones here, as we have seen in the previous experiment, where there were EfficientNet B0 and ResNet 34. In this case, driverless will apply multiple transformers to a single image. And afterwards, it will concatenate their embedding representation together. So if we have two models, then it will generate two vectors for each of the models. And we'll just concatenate them together to obtain a single representation of the image. The second setting is the dimensionality of the embeddings. So like if we are using just the models from the ImageNet, then the dimensionality, like their kind of like the number of features from the embeddings is pretty huge. So it could be like thousands of features. And of course, it could be like too many features for a single image. That is why we are suppressing this feature space to the lower space. And here you could define what is the number of dimensions you want to use in your embeddings. So in this case, again, you could select multiple values, and it means the driverless will use multiple of them and concatenate them together if needed. So it will decide what is the best value and maybe concatenate them together. And one more important setting here is this enable fine-tuning. So as we have discussed, driverless allows to fine-tune their image transformer for a couple of epochs. And by default, it is disabled. However, you could enable it. The limitation here is that it requires a little bit more time compared to the usual like transformer without the fine tuning. It means that probably it is better to use the GPU machine, the machine with GPUs, in order to use this for the modeling. And also you could specify the number of epochs that you want your model to be fine-tuned for. And in this case, like 1 or 2 epochs is usually enough because we are not actually training the models end to end. But what we're doing here is that we want to go from the ImageNet weights to the weights that are closer to your data set. And in this case, just 1 to 2 epochs is enough to get better representations. And finally, for this fine tuning, you could also select the list of the augmentations. So by default, we are only using the horizontal flips. However, you could also select some additional augmentations if you know that they work for your particular domain. And again, it will allow the image transformer to generate a better embedding space. Yeah, so it is just major settings for the image transformer. And it is all about this this first approach about the image transformer. So do you have any questions here? Let me see. Okay, I don't think so. All right, so now let's move on to the second approach, this image outer model approach. In this case, we also start with the usual driverless experiment. And for example, I could use some different data set here. So for example, here is a data set with their people, and we need to detect whether a person is wearing a mask or not. And we have just two labels, whether like the mask is on or off. So it is just a binary image classification problem. And here we have only the image feature. So it means that we do not need to apply this image transformer, as we will have only the images, and we do not want to use it with mixed data types. And that is why we could use this image outer model approach. So for this purpose, you could start the experiment, again, clicking the predict. Here we have only 2 columns, image and target. So we select the target as our target. And in order to change our approach from image transformer to image model, we need to go to the expert settings. And here we have a setting called pipeline built-in recipe. So it represents different pipelines. And here you can select this image model pipeline. So once it is selected, you could click save, and it will update the preview. And here, instead of the usual driverless preview, you will see the preview that corresponds to their automatic image model. In this case, it says that it will use just image outer like model for the modeling, and it will be just a single model. So it means that in this case, we are not using the genetic algorithm that is used by driverless under the hood, but we use some specific optimization techniques for the deep learning models. Also, in the preview, you could see the list of the architectures that we will try. So in this case, you could see that it is DenseNet, EfficientNet before, ResNet, and so on. And here we could control this list with their accuracy knob. So if you change the accuracy knob and if you make it lower, then we will use their smaller models. So in this case, you could see it is ResNet 18 and ResNet 34. So they're pretty small. However, if you're increasing the accuracy, then we will try larger models. And here you could see that it is SERESNext 101, EfficientNet B6, and so on. So it means that you have here a control of what are the architectures you want to use. And of course, the trade-off here is the time and quality. So like the larger models will probably produce better quality, but they will be very slow during the like training and inference. And if you have some fast deployment setting, then probably you should go with smaller models, but probably the quality could be worse. And another setting that controls the image outer models is time. So here, by default, it is 2 here. And you could see at the preview that we'll be using the 4 models for the modeling. So we'll basically try 4 different models to select from. And for the final pipeline, for the final ensemble, we will use just a single model. However, if you're increasing this number, then we will try more models. And for example, with time setting 6, we will try 20 different models. And for the final pipeline, we will use up to 3 models for the ensemble. So it means that we will be ensembling multiple models or multiple checkpoints from a single model. And the final model will consist of up to 3 models like in the ensemble. And afterwards, once you're satisfied with the results of the preview and you have uploaded your dataset, then you could just click again, launch the experiment, and it will start this image outer model experiment. And again, I have pre-run a couple of experiments before, and here is this experiment with a mask detection. So what you could see here is that it looks as a usual driverless experiment. So we could also see here the iteration data. We could also see all the rock curves, all the plots, summaries, and so on. The only difference is in the variable importance. So in this case, as we are using this image outer model approach, and we are using just raw images as an input to our model, then always in the variable importance, we will have only a single feature that represents our image. And it will be used for the modeling. And on the iteration data, each point represents a single model or a single checkpoint from the training. And here you could see in the name of the models, the name of the architecture. So in this case, it was SE ResNet 18, and also the cropping strategy. So in this case, it was crop. And you could see here that we're kind of like increasing the quality and changing the models. And the final like individual in this iteration data is called ensemble TTA. So what it means is that in the final like kind of step, we try to ensemble multiple checkpoints together. And if they produce better quality results, then we're ensembling them together. And it kind of allows us to firstly generate a better quality model, and secondly to make the model more generalizable and more robust to the test datasets. And the second approach with the same purpose is called TTA. It stands for the test time augmentations. It means that instead of just inferencing the models on the pure test images, what we are doing is we firstly make inference on their initial image. And then, for example, we could apply augmentations, for example, horizontal flip. And we also make the second inference on the horizontal flipped version of the image. And afterwards, we're averaging the results of these two predictions. And again, it allows us to make the model more robust and kind of make sure that it works even for augmented images in the dataset. And another addition to these image outer models is the tab here called Insights. So it is here on the right of the screen. And once you click it for the image models, here we have the additional information about what was the best single model during the modeling process. And it kind of like gives us more idea of what is actually going on inside the modeling. So in this case, you could see that the best model for this experiment was ResNet 18 with a batch size and the cropping strategy resize. And also we were using like Adam optimizer. Also, you could see the plots by the epoch. So instead of just having the single number that represents the quality of the whole model, you could see how the quality, the training and validation losses were progressing from one epoch to another. And also the same is for the metric. So in this case, we have selected rock AUC metric, and you could see how it is progressing during the training. Apart from that, we're also showing some images. So firstly, we're showing just some sample train images. So just a random sample of images from the dataset, and you could see what is the size of the input images and what are the labels of the images there. Then we're also showing the sample augmented images. So in this case, we're kind of like showing the user what actual augmentations we have applied and what model like treats as their like best set of augmentations for a particular data set. And in this case, you could kind of like could look at these images and just to make sure that all these augmentations are making sense for your particular domain. Also, we're showing the validation errors. So if there are some validation errors in our validation dataset, then we're showing the true label and the predicted label. And we could see where our model is making the errors, or we could potentially locate some errors in our data labeling. So we have some incorrect labels in the dataset. Then we could probably see them here. And finally, we're showing their GradCam visualizations. So the GradCam like allows us to kind of draw a heat map over the image and to see where exactly the model was looking at while making one decision or another. So for example, here in the first image, where we have masks all over the image, it kind of like looks everywhere at the image. However, if we have like some specific regions, we could see that they're emphasized and where the model is looking at while making the decision where the person wears a mask or not. And again, if there are like multiple people in a scene, then it kind of tries to look at all of them. So again, it kind of like allows us to get some interpretability from the image model and to make sure that it looks at the details that are important to our model. And it is not overfitting to some other irrelevant features. And just to showcase you the diversity, as I said, we could work with absolutely different problem types and data sets. So here, for example, I have a use case with predicting the BMI index. So the idea here is that we're providing the image of the person, and we're also providing some tabular features. For example, here, I'm providing just the age. So I have age and image of the person. And the model tries to predict the BMI index of this person. And in this case, you could again see that together with the images, it also uses the age as a like most important feature to predict the BMI. Another example with image modeling could be some medical applications. So for example, here is a data set with histopathology images. So in this case, we have like 20,000 images. And here the problem was also just a binary classification. That is why the metric is ROC AUC, and it performs pretty well on this particular data set. And again, we could go to the insights and we could see what's going on inside this model. And you can see here that the data set has completely another domain, right? In this case, we have some medical images, like histopathology images. But still, the model like tries to find the best set of augmentations, the best set of models to model this particular data set. And also, you could see where the GradCam was looking at for making a decision. And probably a couple of more examples. Yeah, for example, here's a data set with just X-rays. So again, here we have like 5,000 images, and the data set here is pretty pretty easy. And here we need to detect whether it is a pneumonia or not detected in the image. And again, you could look at the insights. You could go through your data set. So in this case, you could see that we have this just X-rays images, and we have two classes of pneumonia and like just normal class. And again, like we could look at the GradCams, and sometimes it kind of like looks exactly where we would expect it to look, like at the lungs areas. However, sometimes it looks just at the edges of the image, and it seems like these predictions are not really confident, and maybe we could kind of like drop them off during the production. And speaking about the production, as I said, for the production, we have two separate like approaches, right? It is either image transformer or image model. If it is image transformer, then it allows us to build the C++ module scoring pipeline. However, for the image auto model, it is grayed out, so we can't use the image the C++ scoring pipeline. However, we are still like Python scoring pipeline is still available. And it is pretty fast. It is still pretty fast for the image models, and it is enough to use Python scoring pipelines for the deployment. And the rest is pretty much the same as for the usual driverless experiment. All right, so probably that's it. What I wanted to show today. So do you have any questions so far? Okay. So probably everything was clear, hopefully. So just a last single piece that I wanted probably to show is, as we have mentioned, that we could work with image, video and audio data as well. And here is an example of the audio classification use case. The dataset here represents just like various general like noises from the nature, for example. And here we have like 77 different classes. And the performance here is not as good as on the previous datasets. So here we could see the metric was F1, and it is about 0.7. So it is still good, but this problem is much harder than the previous ones. And also have like 77 different classes. And if you look at the insights, and the data set that we were using here is actually the MEL spectrograms of the initial audios. So for example, if we have like this like audio of TikTok, then you could see that it kind of represented as an image in the MEL spectrogram, and it looks in in this manner when we have some like no sound, and then these talks of short talks. And in this case, like again, driverless models allows to utilize like even such MEL spectrograms and use them as usual images for the modeling. And you could see also the grad cams are also looking at some like hidden representations of the audios that are hidden in this MEL spectrograms. So if you want to if you have a problem with audio classification, then this approach is also suitable for these problem types. Okay, and probably I could see a couple of yeah. So the question is it available in driverless 190? So yeah, so it is available starting from 190. So basically, like the versions that I'm using here is 1921 for the driverless, but all the features that I was showing today are available starting from 190. Yes. Okay. Any other questions? Yeah, the next question is how do we deploy these models and with the module? So the idea here is probably you had some previous sessions on driverless, and it was already covered a bit, but I'm not sure. But the idea is basically if you have some finished experiment in driverless, and for example, we could open this like car prices. Then here we have like two buttons: download Python scoring pipeline and download module scoring pipeline. And what they represent is, yeah, you could just click it and it will start the downloading process. And inside we have like this scorer zip archive with also like instructions and readmes what you should do with it. And basically it allows you to kind of like incorporate it into your code, like into your like kind of framework, or into your like just as an API, for example, for to get predictions from the model. And it allows to use either like Python or Mojo. So we have both C++ and Java modules. And it allows you to utilize these models in your production setting. And it allows you to get predictions from the trained model. So basically all you need to do is you need to prepare the similar data set that you were using for the modeling in driverless. And then you could pass it in different forms, as either like just as a request or as a like CSV file. And afterwards, it will output the predictions back. And for the like image transformer, we have both these options available. However, for the image auto model, we have only Python scoring pipeline available. So it means that it works only in Python. Okay, so hopefully I have answered this question on the deployment. So if you have any additional questions, please ask. Yeah, all right. So the next question is, can we use these image data sets are they available publicly that you could use for the modeling? Yes, they're available in our public S3 bucket. So I guess we could share the link to this S3 bucket together with the slides after this session. And here on the S3, you could see these different data sets. So we have like different use cases, different data sets here. And I guess all the data sets I was using today for the demo are already here. So yeah, so you could just directly like upload the data sets from here and use it for the modeling. Okay, the next question: what are the new models on the roadmap in terms of time? So basically, like here, I will open this slide with a roadmap. So here, as I have said, we have this classification and regressions that are already working. And here I have this mentions that it works starting with version 190. And for the other problem types, we have this working prototypes. And the next step is to implement it into the product. And like our current estimate is kind of like this year. So I can't give more strict deadlines, but yeah, but it is definitely this year. Okay, the next question is, can we deploy a CV model in real time with REST API on Steam? So it is probably better to ask someone else. I don't think that I have a good question. So I mean, I'm not really familiar with the Steam, but yes. So I mean, it is better to ask this question someone else. So I'll probably ask it. And again, we'll follow up with an email with all the details there. Yeah, I'll probably copy it. Okay, any other questions?
Okay, I think we don't have any other questions. Thank you, Yauhen. Thank you so much. This was a great session. I'd now like to introduce Rahul Gupta, who is our SVP of Healthcare and Insurance at H2O. He will be talking about where AI is making a difference in the industry, what are the challenges, and what business leaders can expect. So please join me in welcoming Rahul Gupta.
Thank you, Bruna. To the Aetna CVS team on the call. I hope you guys had a wonderful 5 days of sessions. I'm sure a lot of you are very excited about trying it out. Probably you're already kind of on that road. And I think over the next couple of weeks, you will get a lot more insights into the platform, try it out and things like that. So I think we are on the last day as far as the trainings and the talks are concerned, I believe. So I wanted to take a slightly futuristic view or moving forward view from an overall AI point of view. So let me see if I can share my screen. Yes. Okay. So can all of you see what I have on the screen?
Yes, yes, that's perfect.
Thanks, Bruna. So I wanted to take, because, look, all of us are striving towards this, this common goal that whatever we do in our day-to-day work in terms of developing algorithms, solving new challenges, eventually they are all going to make a difference in the world of business that we live in, whether we are in the healthcare space, retail space, manufacturing, whichever industry we take. And I think more healthcare in this particular forum. But at the end of the day, we all want to move into a road where everything that we create is adopted and it brings, return on the investments that have been done. And, today what I'm going to do is I'm going to talk about what some of the industry best practices are. How do you address some of the challenges of actual adoption? And I know some of you might, might be already be a part of these strategy sessions. Some of you might actually be thinking about execution and things like that. So I will also use some cross-industry examples because I know healthcare is surging forward, but in some aspects, there are some other industries also who've taken a little bit of a lead. So let's learn from all of them. And, please feel free to put in your questions. We'll try and answer as much as possible. So this is a slightly different track from the technology track that you've taken so far. And I think eventually, all of you will slowly move into that, because that is the eventual goal of all the work that we all jointly do. So here are some trends that are coming out of the industry. It's good news for all of us. It's not a situation where people are just looking at AI as something exotic that comes out of the whole environment, but this is looking at something which is actually really driving business value. And these are almost 500 executives were interviewed, and actually this is within the health space, and almost 59%, you can see a increase on the left, now actually strongly feel that they would actually be able to get all the ROIs that they have looked at. This is further broken down by subdivisions, so life sciences, health plans, employers, hospitals. And actually, I've heard a term very frequently that, with all due respect, COVID-19 is the biggest chief digital officer in the world today. The amount of change that COVID has driven is unbelievable. There is nothing sacred anymore. Everything is up for betterment, for change, something which people would, how many of us thought that if we don't go and meet people physically, nothing would get done? And now for the last 1.5 years, we've actually been executing pretty successfully. So a lot of AI plans have got accelerated. The last is, there are most of the work that we do comes out in two parts. Either it goes into increasing the top line, which is improving health outcomes or patient experiences, or it goes into reducing the cost of care. We know that, a cost of care is probably one of the biggest challenges in any health discussion that you have. And almost 500 executives broken down by these percentages feel that this is going to, this is how AI is going to contribute. Now, this is a very positive message that we have, but let's look at adoption. And here is where we see the challenge. Only 20% of the organizations actually say that they are in the late stages of deployment. There's a little bit of a difference out here. I'm talking about deployment, not development. There are a number of organizations, and I think, correct me if I'm wrong, I think we have almost about 100, strong data scientists who are actually participating in this event. So the development is strong. How do we talk about deployment? And that is where the challenge is today. How do we get what you guys with all your blood, sweat, and tears have created? How does that actually lead to see the light of day? How does it make a difference in the people who are actually working on it? So I'll focus on that today. So these are some key points that really drive enterprise adoption. So when we talk about enterprise adoption is, it is way more, I know technology is extremely important, but there are a lot of other points that you and your colleagues and your leader and the organization is actually looking at. How do you make the cultural shift? It is a cultural shift, and we'll talk about it. How do you set up for success? How do you really get return on investment from what has been created by the great minds that are working together here? How do you then organize for scale? How do you grow it? I'm sure some of you have heard about that. Does it look like a science experiment? Does it look like a mathematics problem that has been solved? Yes, it is, but eventually it is going to change the organization, help the organization that we all work for. Education, lifelong learning. So education is an extremely important part. I know you guys are all very familiar with the power of AI, as I call it. But, a lot of times when you meet somebody in a social gathering and you have to explain what you do, there is a challenge. The same challenge exists in the industry today. How do you basically get all of that together? How do you continuously reinforce that change so that it becomes a way of life? And then what I call as the virtuous circle. It's a self-sustaining circle. So we'll talk about each one of these today. Please keep the questions flowing if you have it, and then we can address it, because you may not remember the question that you have. Just type it in, and at the end, we'll all take it up. So let's talk about making the shift. So the first shift that is, I'm sure, so this is no science, this is more art. So what will happen is some things may work for an organization. It is not prescriptive. You will find that, some things work for an organization like CVS, Aetna, Fortune 100 organizations, some things don't. So these are some thoughts which have been distilled together. And, you might relate to some examples that might have happened in your journey. So the first is, how do we move from a siloed to an interdisciplinary collaboration? So, diverse teams, when they come together, business folks, frontline workers, data scientists, UI UX developers, IT teams, unless they all come together, the success of an initiative may have a question mark on it. And what that really means is that, you might have a situation where an organization allocates budgets by a function or a group, in which case pulling interdisciplinary teams might be more difficult. And maybe in the next time you have that discussion, you might want to push the boundaries a little bit. Because what you are doing is you're taking the first steps or the second or the third steps towards addressing this challenge. The second is from experience-based, leader-driven decision-making. So what happens is that, eventually what you are driving towards is that every person in the organization is supported by the recommendations of an algorithm. So it is really technology and people coming together to make a better decision that probably what the technology could have provided or people could have provided. But, there are challenges. There are people who feel that they have, gosh, I don't want to date myself, but I have like over 3 decades of experience. And sometimes I get into that natural flow. I really know what needs to be done, but sometimes the data speaks differently. So that whole adoption of how you can actually bring all of it together is something that we need to work with. Third is, not everything has all the bells and whistles in the first instance. So an algorithm that we might have created may not address every problem in the first instance. So we need to ensure that culture of taking a risk is brought out. Because if you actually, I'm sure you must have heard about that statement, fail fast, fail soon. But what really does is it addresses some business problems that might later on become costly mistakes. So let's not try and get everything done to the last T before we actually take it forward. Let's start bringing in that culture. That is extremely important. So these are some cultural shifts, making the cultural shifts that we need to bring into an organization. The next one is, how do you plan for success? So when we start doing, the first thing is explaining why. There is a lot of fear, when you start looking at AI algorithms, recommendations, technology. I'm sure Hollywood has not done a good job of really kind of creating that fear psychosis that eventually people would lose their jobs because of AI. The fact is that it actually helps their people do their jobs better. There is a fear. So as leaders and as people who really understand, we need to explain and put everything in a context. So I'll give you an example. So for a retail organization, again, the same challenge. And so how the leaders really framed it is that, look, we are born in brick and mortar. We are moving into a digital world, but we are actually fighting the digital retailers. And so leveraging technology is almost an existential situation. And when you put it that way, people look at it from a larger picture point of view. And that is what helps. It needs to be explained. We need to talk about, in the healthcare world, telemedicine is, there is, I don't have the exact numbers, but I know that one particular organization said that they went from 6,000 telemedicine instances in a year to 90,000. Now, if telemedicine is actually growing at that pace, it comes with its own challenges. How do the offices work? What we are trying to do is we are trying to actually fit a telemedicine into a regular office environment. While what really needs to be done is a telemedicine environment has to be created completely different, not try to fit in. Now, the roles of the office staff, the scheduling staff, all of that will change. All that has to be explained. Each organization may have some unique barriers to change. Let's take an example. Suppose there is a lot of organizations have customer relationships or patient care managers. They actually feel that over 30 years, 32 years, 50 years, they really know the patient, but it might be difficult for them to adopt a recommendation by an algorithm of what is the product that they should actually provide to the customer. So that cultural change, especially in a large organization, might be something that needs to be looked into, that needs to be pushed, that needs to be changed. A lot of times traditional situations have, if I'm a manager, if I have 100 people reporting into me, I'm powerful. If I have 200 people, I'm even more powerful. But that doesn't go with the world that we are living in from artificial intelligence. It hampers the adoption of AI and algorithms and technology. I also want to introduce a concept you may have heard about it already. Is called analytics translators. Now, what does that really mean? Analytics translators are people who bridge the gap between AI and business. It helps. They usually come from business, but they have a good understanding. And some of them, I'm sure some of you automatically are doing that job without really thinking that you are actually doing it. So what you're really doing is you are explaining to the business, to the frontline workers, to the leaders of what is the value that AI brings to the table. How is it translating? How will it help grow the business? How does that technology work? So they are literally a bridge. And I think that concept needs to be developed. I'm sure with a lot of understanding that you have, maybe some of you would actually transcend to actually playing that role also, because it will help the overall cause of adopting within an organization. Next one is budgeting for integration. Now a lot of organizations actually invest in technology and growth and algorithm. That's great. That's absolutely wonderful. It needs to be done. But look at it this way. Whatever gets developed, we have heard a lot of times it never hit production, or even if it hit production, it may never hit ROI. So let's take an example from the industry. And I'll actually give two examples on why this is extremely important. So the first of it is, let's take an example of a telecom and then take a healthcare example. In the telecom world, the algorithms predicted where the churn for customers is going to happen. These customers are actually at a risk of moving to another carrier. So this algorithm started predicting all these models. What are the products that you could take to them? In parallel, what the organization did is, what our customers' organization did is, they actually trained their call center folks and the outreach folks to how to take these, talk to the customers, so that they could proactively offer rather than reactively. When the customer calls that I want to, how many of us have experienced that when I call, I want to switch, they start offering me everything. But if we could proactively go and talk to them, that is when you build relationships. Let's talk about a healthcare example. So, readmissions use case is something that all, if not all, most of us have thought about. Now, algorithms are predicting medical situations where people might be at risk ahead of time based on the information and data and analytics which is available. A lot of work is being done around that. The biggest challenge is, how do you actually have the physician's office or the physician or the nurse call up the patient or patient's caretakers and tell them that this is what we sense from the information that we have. This is the risk that the patient is running. Can you come in for a checkup or a preventive measure? Because the event has not happened. It's a very, very delicate matter. But if that is not done, if we don't create the right scripts, if we don't create the right messaging that the physicians or the physician's office could actually do, then you may not be able to prevent the event from happening. And if you don't prevent the event from happening, the algorithms and the AI technologies, and you guys did the right job. But if we did not push, the ROI never came through because the event still happened. You were not able to prevent it. So I think allocating that part of integration and budgeting is very, very important. I'm sure all of you have examples that you can think of where, my request is start bringing them up in your planning sessions, in your discussion sessions, because that is what will drive, with a vested interest, it will drive more budgets your way, because they will actually start looking at more initiatives, of value that you've generated. And then let's talk about balancing feasibility and time investment. So there will be some short-term goals and there will be some long-term goals that you will look at. A long-term goal may be a few, maybe a few years, and a short-term maybe a few months or a few weeks. You have to balance both, because a long-term may actually be a very fundamental change for an organization. A short-term may be immediate value, which will actually help grow the business. I'll give you another example. So maybe if we have some folks from CVS and they might actually relate to that is, one of our retailers, they were actually going through a change and they wanted to kind of do and optimize the inventory placement and things like that. But they also realized that real value of inventory placements is not going to happen till they refurbish their stores, till they actually do the shelving structures and things like that, which was again a very long-term goal. But they realized that that is very important and they need to go through it. But what they did is they split the engagement in two parts. The first part was recommending some additional product categories and stuff that could go on the shelves, which could yield results. And then the second part was the longer project. So what happened is that there was a quicker success that could come, which would actually feed the success of the project. And then it could go to the longer term. So there has to be a little bit of a balancing act that we have to go on to that. Again, these are things that you as data scientists, as people who are looking at technologies, eventually these are all things which will kind of start playing for you as you start helping the organization move forward. Now, immediately a question comes up is, okay, so how do I organize for scale? As we start growing, as we start building, as we start taking things forward, there is no magic which says that, this is how you should organize and then you'll be successful. Typically what happens is most of the time the leaders look at, okay, this organization where I was there previously or where I know of or I've heard about or I understand, this is how they organize. But typically, usually it's a hub and spoke arrangement. Now, when we say a hub, this is usually head by a chief analytics officer or a chief data officer, a lot of the leadership C-level positions. And that is very important because it helps you, nurture AI talent, get the AI services and software, build AI communities. A lot of those activities get concentrated in the hub. Now, a hub also has a situation where, if the organization is less mature in terms of AI, then they might have a hub. Not saying that if you are extremely mature, you cannot have a hub. If you are looking at more complex, so multiple business units are participating, then also a hub is very important. On the other side, there are the spokes. So what happens is typically some things like adoption, user training, integration, impact tracking. Those are the things which can usually reside in a spoke. But most importantly, there is always a gray area. And those gray areas will be things like, how do you set the directions for the AI project? How do you prioritize them? How do you design the tools? How do you do the eventual testing? And these gray areas can actually sit in either a hub or it can sit in a spoke. It's again depends on organization to organization, but both these structures are equally strong and powerful. The important part is, have we started looking at organizing so that it is not something which is being done in silos all over the place? There is value that is coming in together. And then the last part of this is oversight and execution. So, typically what happens is the best way is to have C folks, from business, from IT, from analytics, all of those together to actually help in that regular governance that you could actually bring up. Now, the problem is, not the problem. There's another aspect which is important is the execution teams under the oversight and execution. So building that team, and usually the best way, again, I use the word usually because every organization is different, is assignment based. So when you're looking at an engagement, when you're looking at a project, when you're looking at a problem that you're trying to solve and work towards, bring a multidisciplinary team. Bring that whole team together, whether it's from front end, from business, from IT, bring all of it together. That is where you get the best value out of it. I think I'll give you another example. I said I'll use some cross-industry examples. Let me take another example from retail. So, you have the merchandising folks and you have the buyers. Merchandising folks are the ones who are really in charge for setting up the shelves and the store layouts and stuff. And the buyers are the people who are really in charge for buying the right products. The algorithm was making the right predictions of what should be bought and what should be placed, but the buyers with no view of the merchandising were really changing and providing changing the inputs to the AI algorithms. And so it would actually not yield the results that were expected because there was a disconnect between the two teams. When it was realized, the merchandising folks and the buyer folks were brought together. And when they started putting the right inputs together, being cognizant of the fact that both were equally important, immediately the ROI panned out. So I think that becomes extremely difficult, important from an execution point of view. We spoke about educating everyone. So, it always starts at the top, the leadership. It's important, a lot of times when we have discussions with C-level folks, and you might ask question, how do I influence a leadership? At some point of time, when there is an open forum, you will realize that there are some ways to make some points. But leaderships, they really need to understand that they also have to get an understanding of what AI is capable of, what it is not capable of, what they should be looking at. How do you prioritize? Because that really gives an understanding of how to support your efforts. That's extremely important. On the analytics side, of course, the latest technologies, the skills, you really work on that. Then I talk about translators. So translators, these are the analytics translators that I mentioned earlier. And you could actually have people drawn from business or analytics to actually do this. And where they need to have an understanding of, how these analytical approaches are worked, how you basically get all the AI initiatives together, how is it going to impact the business, bringing the business impact back. And these are, again, very truly bridge, so they need to understand both sides of the equation. And then finally, a lot of times, algorithms are pushed out without end users actually having either an input or a complete understanding of how it is that will change the way they do their business. How will it help them? That is very, very important for them. How do they use it? How do they leverage it? Those are extremely critical. So I think education, we all know you are from a very strong academic background. You understand the importance of education, but it is important all across the spectrum. So we've spoken about a lot of points so far, but you have to continuously reinforce the change. Yeah, I'm not a big health freak, but somebody sometimes said that a good habit in a gym becomes a habit after you spend 21 days. So in this environment, 21 days, you are reinforcing that habit to basically become a part of your psyche. Similar thing you have to reinforce every time. You have to walk the talk. As some of you might be leaders, some of you might be doing the AI work, you have to constantly demonstrate that you believe in what you are saying. You believe in bringing that change. You believe in encouraging people who work with you, for you, across you, all of that. You have to walk that talk. The second part, which is sometimes controversial, but look at it this way. Eventually, all algorithms, work, technology that we do is created to support business. Either it could be growth, bringing down costs, increasing top line, making the process easier. So if eventually businesses have to be benefited out of it, shouldn't they be accountable for it also? Because it is important to have them accountable. I'm not saying accountable, because it should not be a situation that if we build it, they will use it. That becomes a fundamental problem from an adoption point of view. So a lot of technology teams own engagements, but I feel that business teams should definitely own those engagements and then help drive along with the analytics team. It makes them responsible for the output, adoption, and ROI. Comparing some results with what was happening earlier to now, I think that is also important because, as we all know, nothing speaks like data. When you have numbers, when you have output, when you have results which are tracked, then it becomes extremely important. There is also one more point in this. Sometimes tracking and facilitate adoption becomes difficult because of the interface that was happening. So you have output, and I don't know whether you are familiar with the dashboards that we have created in terms of AI apps, which becomes easier for businesses to consume. But also, let's look at it this way. Let's give you so when you are creating some AI algorithms predicting some patient cases, unless they are integrated with the dashboards that the physicians or the hospital staff is using on a day-to-day basis, it becomes extremely difficult for them to go to another dashboard or an output and look at it and act on it. It has to be integrated into that workflow. If it is not, it may not get used. And the algorithm is right, the predictions are right, the intent is right, the cross-functional teams were right, but the facilitating that adoption did not happen because of that integration. So when we think about a project, when we think about a plan, when we think about an adoption, we should look at that also. And then lastly, change is difficult for people. It is scary. It is not easy. So there has to be provide incentives for change. And incentives doesn't mean numerical, financial incentives, recognition, commendation. All those are extremely important, a pat on the back, because a lot of us are self-motivated, self-driven. Then it becomes extremely important for us to continue. There will be failures. It will not work out in the first instance. I'm sure you all know it better than I do, that, it improves over a period of time. So that providing that positive instances for change is extremely important. So we've spoken about a lot of things. So let's talk about, is it a self-sustaining circle, a virtuous circle? So, let's start at the bottom. So functional and interdisciplinary team, when you start bringing the whole team, the power of the organization together, what really happens is that you move from solving discrete problems to big picture enterprise solutions. Rather than customer segmentation, you start looking at customer journeys. How can that be improved? Which then leads to the speed of innovation. The whole change starts accelerating. And then what you really get is AI-enabled decision-making at the front line, which finally leads to a return of investment and adoption. And this becomes a circle that actually continues throughout. It's almost like a virtual circle. So I know this, I hope this made sense. And, you know, I'm a big fan of Robert Frost, and there are a couple of quotes that I really like from him, but this one I think is very relevant because, you know, you all have taken a path which you've been on this journey. You've created, this is something which is actually, you could have taken the easier path, but you've chosen the more difficult path. And I think that is what is going to make all the difference. So I end the talk a little bit. I hope I was able to communicate some thoughts with you. Very happy to answer any questions. I did put my email address also on that if you want to reach out. Bruna?
Thank you, Rahul. Thank you so much for this great talk. We're excited to have you all here. Thank you so much for joining us this week. And I'd like to bring Nikki on if she wants to share any relevant information around the next steps. And
yes,
Rahul, you can stop sharing your screen if you'd like.
Okay, I'm going to do that. I'm just trying to do. I suddenly became technologically challenged. Okay, I did that.
That's perfect.
Thank you, Bruna. Thank you, Rahul, for this wonderful talk. I really enjoyed it. I hope the audience also shares my feelings. Very, very important insights, talking from a technologist perspective. I think this was really excellent. Thank you so much for this. Now, this is the wrap up of our training sessions, as well the end of the official Hackfest week. We still have the 2 Q&As at noon and at 3 p.m. Please drop by, ask questions, come in with your use cases, or just meet us. This event has to be virtual again this year. Hopefully next year we can meet everyone in person, but if you want to say hi, please. The next month, coming month, you will have access to Driverless. Those of you who have already started using Driverless, you can keep using your profiles and working on your problems. We are always available via the Aetna _QA at H2O.ai. We will not have open hours for the month, but please reach out. And if necessary, we can also arrange some calls. At the end of that, there will be more announcements about what to expect. We have some exciting plans to wrap up of the bigger Hackfest event, 1 month long. Thank you all so much for joining. It has been a pleasure.
Thank you. Bye.